present our work, NEMTO, Neural Environment Mapping for Novel View and Relighting Synthesis of Transparent Objects. The goal of this project is to create the first end-to-end neural rendering pipeline to model 3D transparent object with complex geometry and unknown indices of refraction. Previous method on the problem of neural inverse rendering focus on decomposing scene intrinsics, such as geometry and surface reflectance modeled through diffuse and specular component, and thereafter recreate the scene through differentiable rendering under modified scene parameters. A common assumption used here is that objects are all opaque and do not allow transmittance of light. However, transparent objects follows smooth dielectric material and takes their texture from environment and can change appearance with varying view direction. Therefore, they cannot be modeled through diffuse and specular component. The consequence of following inaccurate assumption can be that first, we'll infer incorrect texture, which is dependent on environment illumination. Secondly, it would be impossible to relight or modify scene intrinsics for transparent objects, as they are handled incorrectly in the first place. And lastly, we would have inaccurate geometry as they are entangled with their appearance. Therefore, I hereby reiterate our goal, which is to take into account the material properties of transparent objects and create a representation that allows novel view and relighting for this kind of object. From comparing with previous work, our method seems to be the most capable one with the most flexible setup. Our work can model refraction, allow novel view synthesis and relighting without providing additional information, and model detailed object geometry without requiring complex physical setup for capture, as indicated by previous work. However, one limitation of our work is that our work cannot jointly estimate environment illumination along with geometry and appearance during training. The key contribution of our work is that we propose a physically guided ray bending network that disentangles object geometry and light refraction. We choose this implicit sign distance function as the representation of our geometry for more efficient storage than explicit representation, and also for accurate surface intersection point rather than radiance field, which makes the first module of our pipeline. Our ray bending network takes as input the viewing direction, surface normal, and intersection point, and output final refracted ray direction, which makes the second component of our method. Finally, our differentiable rendering method is a physically inspired approximate of the true radiance emitted by each ray through the Fresnel term. After calculated the rendered RGB, we compare it with ground truth for photometric loss, but that's not our only loss term. Additionally, we have ray refraction estimations followed by refraction guiding loss and the patch-based refraction smoothing loss to encourage locally smoothing refraction directions. For our geometry optimization, we follow the same pipeline as our previous work. For our results, NEMTO is tested on both synthetic and real-world dataset to prove its ability to create high-quality novel view and relighting synthesis. We show qualitative results here. For a quantitative comparison, please check our paper for details. As you can see, NEMTO synthesizes high-frequency detail for refraction better than the baseline method. Thanks to our successful disentanglement of appearance and geometry, NEMTO renders relighting without mistakenly taking into account previous illumination, as indicated in the circle region. Our method is also robust on transparent objects with various indices of refraction. For real-world dataset, our method adapts to this kind of data captured with handheld camera in real-world setting. Despite inaccurate camera poses and illuminations, NEMTO can synthesize visually plausible renderings for the desired object. We have presented NEMTO our work on modeling transparent objects. For a detailed experiment and methodology, check out our project website.